All right, good morning. It's day 6 of the probability unit, and we're going to be looking at the multiplication rule of probability, or sometimes called the product rule of probability. So from the day before, the addition rule for probability was that if you're trying to calculate the probability of A or B, also A union B, you can use those both. It's the idea that probability of A or B is equal to the probability of A plus the probability of B, and then minus if there was any overlap. So that's the probability of A and B. And then using symbols, just to remind you, that's the union one. This would obviously all stay the same. Oops. And then and is the intersection. So it's the upside down U. It almost looks like an A if you were to put like a little bar across it. All right. And then over here, if A and B are mutually exclusive, that means there is nothing in the overlap. So you wouldn't have to do the last subtraction piece. In that case, it would just be the probability of A plus the probability of B. Done. Right? So it's even easier. But a lot of times there is something in the overlap, which is why we have to include that. And it says we're going to discuss the multiplication rule for probability, which is used to determine this little guy right here. So it's saying in the last class we saw the product test for independence. Right? So the test for independence was the idea of the probability of A given that B happened. Is that the same as just the probability of plain old A all by itself? All right. But we had to figure out, well, how do you calculate this conditional probability? So that's probability of A and B over the probability of B. And then is that the same as the probability of A? And then we did that last little step to cross multiply and said, hey, that ends up being probability of A and B comes out to be probability of A times the probability of B. So what it loosely turns into is if it's or, you're adding. If it's and, you're going to multiply those probabilities together. So that's kind of like the short way to remember it. Right? And it's saying this means if A and B are independent, we can figure out that to get the probability of A and B, we're just going to simply multiply the individual probabilities. So I think at the start of yesterday's notes, we looked at like the probability of picking like the red cube out of the bag, and we found the individuals. And then what we would have done is just multiply those individual probabilities together. All right, but you'll see that in today's notes. Says, what if A and B are not independent, or what if they're dependent on one another? So in that case, what you would do, and I don't want you to overthink this one too much, but in that case, if I think that if the probability of A and B, the probability of A times the probability of B when they're independent, then all we would change for this is, let's say they're not independent or they're dependent, then the probability of A and B, you're still going to use, let's say, the probability of A, but then the second part will just change a little bit. What's the probability of B given that A has happened? All right. Now, the notation makes it look really fancy, but all I want you to think about is if the events are dependent, how does this number change based on that one? And when you see some examples of it, you'll realize like, oh, this isn't super tough. But this is when the events are not independent or they are dependent. All right. So down at the bottom, when it says if A and B are independent, then it's simply going to be that the probability of A and B will be that you multiply them separately. Done. If they're not independent, then the probability of A and B would be the probability of A times the probability of B given that A has happened. Now, keep in mind, we could rearrange this. We could say the probability of B and then times the probability of A given that B happened. So don't get hung up on the order, because we know and is interchangeable, kind of like multiplication is commutative. Same thing here. So it's either A times B given that A happened, or B times A given that B has happened. All right. So come back to a simple example. We've got our little spinner guy here. It's saying, let's think about our friend the spinner. If we spin more than once, are the outcomes independent or dependent? Right? They're going to be independent. again, don't overthink it. Don't worry about like, oh, but maybe it started on the 3, so it's going to land here. No. All right. It's just equal chance of landing anywhere regardless. All right. So there's an equal chance of landing, I'll say anywhere on spin 2. All right. It has nothing to do with spin 1. What is the probability of spinning an even and then spinning a 7? All right. So spinning an even and a 7. So it's pretty shorthand here, but hopefully you get it. Since we said that they are independent, that's just going to be the probability of spinning an even times the probability of spinning a 7, right? So think about it. Even, you got 2, 4, 6, 8. You have a 4 out of 8 chance there. Probability of spinning a 7, well, there's just 1 7 on the board out of 8. And now we know we're just multiplying those together. Could you simplify that first? Of course you could. Otherwise, 4 out of 64, either way you do it, it'll come down to be 1 out of 16. So there's the chances that in 2 spins, you would land on an even on one spin and then a 7 on the next spin. And now keep in mind, that's theoretical. We didn't actually do a trial. That's in theory what would happen. All right, what's the probability of spinning a 7 and then spinning an even? Well, even though I can write it differently, it would come out exactly the same. Just in this case, it'd be the 7 first and then the even. So it'd be 1/8 and then times the 4/8. And I would still get the same darn answer because we already said it's commutative. So what's the probability in 2 spins that you spin a 7 and an even? In this case, they're not specifying the order. So you could get here the even first, then the 7, here the 7 first, then the even. And so technically here, since you have to consider both cases, this is like saying getting a 7 and an even, or an even and then a 7, you would add those probabilities together. So it'd be 1/16 plus 1/16 for a total of 2/16 or 1/8. All right. Because technically you'd have to consider what are the different ways that it can happen. Just a little tricky. Sometimes it's tough to think about that. All right. Let's see this next one. Suppose a power generating facility has 3 primary safety switches in the case of emergency. Okay. Probability that any one of the switches would fail. So like power shuts off or doesn't work or something is 5%. What's the probability that all 3 will fail? So we want to know what's the probability that like the first one fails and the second one fails and the third one fails. Now, you don't really have to write it all out, but I just want you to think about it so that what you're really doing is when I'm saying and, that's how I know I'm multiplying. So the probability of the first fail, and then times the probability of the second fail times the probability of the third fail, right? And they're saying that they're all independent. So it's not going to change. So this would be 5%, this is 5%, this is 5%. Remind yourself, go back to decimals, 0.05 times 0.05 times 0.05. So if we multiply that out, grab my calculator over here. I can, of course, do 0.05 times 0.05 and so on, or I can do 0.05 cubed. 1.25. And then it says e to the -4th. Remind yourself, that is 10 to the -4th, which really means 1.25. I'm moving the decimal back 1, 2, 3, 4 places. That's the probability of all 3 switches failing, which is what it should be. It should be really, really low. You wouldn't want all 3 switches to fail. So you'd want it to be essentially 0 if you could get it there. All right. For number 3, suppose that a credit card company states that when a customer is selected at random, the probability that the customer pays his or her bill in full each month is 0.35. You should do that if you can. The probability that a customer makes regular online purchases is 0.83. And then, and the 2 events are independent. Okay. So they're just saying that like you're not more likely to make purchases if you pay in full or vice versa. They're just completely independent from one another. All right. What is the probability that a randomly selected customer pays his or her bill in full each month and makes regular online purchases. All right, and right there means we are going to multiply. So the probability of the 1, so the 0.35 times 0.83. And of course, we could write it out all nice, but as long as you get the gist of what's going on here, we multiply it out, we get 0.2905. So that's the probability that you pay on time and you make online purchases. So, they're saying about 29% of people do that. All right, what is the probability that a randomly selected customer pays the bill in full each month or makes regular online purchases? Okay. Or we said translates to, we are going to add. But what you want to remember is from the first page, and I can bring that right back here. When we are adding, you have to add one plus the other, but then subtract anybody that's in the overlap. And we got right here, we got about 29% in the overlap that do both. So you have to account for that. So you're going to add the 1, the fact, move my decimal point there. You're going to have the people that pay their bill in full plus the people that make online purchases, but you've counted those people twice. So now you have to subtract the 0.2905. All right. So this is like the probability of A plus B minus the probability of A and B, right? And you would have figured it out anyways, because if you went 0.35 plus 0.83, you're over 1. You can't be over 1. So that should tip you off to like, wait, what did I forget about? So then minus 0.2905, and we land at 0.8895. Right. Now it's the notes, so obviously we don't have to stress too much about where to round. But if the homework doesn't specify, try to keep it as exact as possible. There's no need to round that. Just leave it exactly as it is. On the quiz next week, I'll tell you where to round. All right. All right. Let's move on to the next page. Ooh, we're going to an Algebra 2 class. Imagine that. We've got 13 girls, 11 guys. 3 lucky students will be randomly selected to go on a math field trip. Woohoo! To spend the day with the New York Yankees statistician. Actually, that would be very cool. So it's saying here, sorry, let me just find my correct notes page to look at. There we go. What is the probability that only girls are picked? Right, we have a couple more girls than guys, but still the chance that only girls are picked, right? It's definitely not going to be, 100% of the time. And it says we need to answer some questions before we can actually start that. Okay. What are the 3 events that must happen? Well, that means you would pick a girl first and then another girl, second, if you will, and then another girl third. All right. So picking a girl and picking a girl and picking a girl. All right. The reason we draw this out, you need the ands in here. So, and it says, are these events independent? Why or why not? Well, think about the probability of picking a girl the first time. There's 13 girls to pick from. Out of this would be 24 total. If you pick the first girl, you can't pick her again. So as soon as she's out of the mix, the probability of picking a girl the next time, it now changes. It would only be 12, and there'd only be 23 students. So if the first event happening then changes the probability the second time it would happen, or for the second event, that's the definition of events being dependent on one another or not independent. So when it says, are they independent? The answer would be no, right? And because what we just said, right? Because once a girl is chosen, she can't be picked again. I'm going to use a little ... Therefore, the probability changes. Right. So when it says use the multiplication rule to determine the probability of only girls being selected, I don't want you to get all crazy fancy with the writing. Right? But on the first page, we had said, all right, if they're not independent, then the probability of A and B, you're going to do the probability of the first thing, but then times the probability of the second thing given that the first event has occurred. So all it means is we're just going to change this number, all right? Could I write it using all the fancy notation? Sure. Super not necessary, all right? So the probability of, girl number 1, I know that didn't make sense the way I wrote that, but would be 13 out of 24. The times the second girl, all right, now it's going to change a little. It's not going to stay 13 out of 24. It's now going to be 12 out of 23. And then times the probability of, girl number 3. Well, now there's only 11 girls to pick from, and there's only 22 kids to pick from. So that's all that means, is that you have to realize, like, oh, hey, it's going to change. It's not just the same thing times itself over and over again, all right, like it was in the switches question. All right, so we got 13 times 12 times 11. So our numerator, let me move that out of the way, 17, 16. Our denominator, 24 times 23 times 22 over 12,144. Now, of course, this thing will probably simplify, so divide it, and then math frac, and that comes down to be 13 out of 92. So as a quick reminder, don't forget when you're multiplying fractions, you multiply the top together, the bottom together. You can do it all at once on the calculator, you choose, all right? But that's the chance that the first person would be a girl, the second person would be a girl, and the third person would be a girl, all right? How can we determine the probability of at least one boy being selected, right? If you think about it, if that's the chance that it's all girls, then every other scenario has to have at least one guy in it. It might have one, it might have two, it might have all three. So think about if that's the case of all girls, and they figure out every other case, well, all the cases total should add up to 1. So if I want to find the probability of at least one boy, it's 1 minus the probability of all girls. So 1 minus 13 out of 92 is going to leave us with 79 out of 92. There you go. So sometimes you just have to get a little crafty and thinking, like, how would I calculate this? Rather than trying to calculate all the cases where there's 1 boy and then 2 boys and 3 boys and add them all up, just take out the cases that don't have any guys in it. All right, last page of notes. We're back to a bag of marbles here. We got 12 red marbles, 8 blue, 5 green. It's saying if 3 marbles are pulled out, find each of the probabilities. In each, we specify either replacement, that the marbles go back, or no replacement. So you have to think about how does that affect the independent versus dependent kind of status there. Oops, sorry. So it says find the probability of pulling 3 green marbles with replacement. So you pick it up, you're like, hey, look, it's green. You put it back in. So this next time you go to pick out another marble, the probability isn't going to change. So because you're replacing it, that means that they're independent, all right? So that means when we want 3, you're just going to take the probability of green, probability of green, probability of green, and the probability does not change one bit. So it's 5 green marbles out of, that would be 25 total. And then same thing here, 5 out of 25, 5 out of 25. Right? And so you can, of course, reduce each one of those to 1/5. And so then 1/5, oh, we don't even need a calculator. 1/5 cubed. 1 cubed is 1, 5 cubed is 125. So is it a high chance? No, it's less than 1% right there that you would, assuming you're not cheating and you're not looking, that you'd pick out a green marble each time. All right, find the probability of pulling out 3 red marbles, but without replacement. All right, so if I don't put the marbles back in, each time I take one out, there's less marbles in there, which means these are not independent or they are dependent events. So you just have to remember the probability is going to change here. Now, technically, we could say like probability of red times the probability of red given that the first one was red, probability of red given that the first, 2 are red. Do you really need to write that down? No, just think about how the numbers change. So the first time chance of getting a red marble, there's 12 of them out of 25. The next time you took out a red marble, so there's only 11 in there, and there's 24 total. You kept that one. Now there's only 10 out of 23. So don't worry about this part. Focus on that part, all right? And then multiply it all out. If you trust my calculations, which I hope you do, would be 1320 over 13,800, and that'll reduce to 11 out of 115. Right? And if you're looking at that and you're like, oh, what is that? You can always divide it and get a decimal to give you a better idea, percentage-wise, what that is. Last part, find the probability of pulling out 3 marbles of the same color without replacement. Right, now they didn't tell you what color to do, so you have to consider, what does that actually mean? If I want the same color, what that could mean, all right, for the probability of the same color is that they could be all red, which we just calculated a second ago, so awesome. Or they could be all green, or they could be all blue. In a case like that, you have to calculate each thing separately, and then the or means that we add them all together. So we already did this one. This was 11 out of 115, plus the probability of all green. Well, it looks like we did it, but that one was with replacement. This one's without. So the first time you pick out a green, there's a 5 out of 25 chance. If I don't put it back in, it's then 4 out of 24 and 3 out of 23. And then play the same game over here for the blue. There's 8 blue marbles. So there's an 8 out of 25 chance the first time, 7 out of 24 the second time, 6 out of 23 the third time. So let's calculate each of these and then add them together. So 11 out of 115. This guy comes out to be, if you multiply and simplify, 14 out of 575. Oops, I take that back. I was cheating and using my notes over here, and I have my notes in a different order. So that is not 14 out of 575. Just kidding. The all green, this one comes out to be 1 out of 230. And then over here, this one comes out to be 14 out of 575. All right. Either way, add it all together, math bracket, it's 143 out of 1,150. That's the chance that they'd all be the same color, because they could be all red, all green, or all blue. And that or implies we're adding them. Right? The very last question. Woo, you made it. Find the probability of pulling out 2 blue marbles and 1 green marble in any order. All right, this is the trickiest of the questions because, again, just like the last one, you have to stop and think, what are the ways that it can be done? All right, since it says any order and it's just 2 blue and 1 green, it could be the order they just said. So 2 blue and 1 green. Or maybe you pick a blue and then the green one happens second and then a blue one. Or the green one could have happened first and then the 2 blues. So you have 3 cases to consider. So if you calculate, let's say the first case, since we are with replacement, that means that there's always 25 marbles to pick from. So like the first time, there's 8 blue out of 25 times, there would still be 8 blue out of 25, and then times green would be 5 out of 25. Or means we'd add it to this next one. But if you think about this next calculation, just because I'm changing the order doesn't mean I'm changing the numbers. The blues are still 8 out of 25. The green is still 5 out of 25. So what you can start to see is that this number, I'm going to get the same thing here. I'm going to get the exact same thing over here. So all I have to do is calculate it once. So if I calculate it once, I've got, let's see, 8 25ths times 8 25ths times 5 25ths. So that's what I meant by you can do it all at once and just math frac that guy. So that would be 64 out of 3,125. But then so would this, and so would this. And so when I put together, I'm really just multiplying it by 3. And that would come out as 192 out of 3,125. So this last page, it gives us some different things that you have to consider, some different cases, right? So when you try the homework, reference back to these pages, see if that helps. If not, you let me know, shoot me some emails. Those are the ones that I'd be happy to put on the website, the full solutions, if you feel like it would help. All right, have a great day, guys.